begin. This is E658 lecture 46. So yesterday we were looking at the behavior of a first order continuous time delta sigma modulator, and we concluded that not much is lost. In fact, nothing is lost if we assume that the sampling rate Fs is 1 hertz, and you have and the signal bandwidth of interest is 1 by 2 OSR hertz. All right. So today let's take a look at another important feature of this first order modulator, and that is what happens to it when you put in the as I mentioned yesterday, the desired signal band is basically the in band frequencies are basically 0 to 1 by 2 OSR, right, because Fs is equal to 1. Now, the bands which will alias into, in a conventional Nyquist type converter or an oversampled converter operating on samples of U of t already, what all frequencies will alias to this band? So, frequencies of 1 plus minus 1 minus 1 by 2 OSR to 1 plus 1 by 2 OSR, alright, at the if I make this k, where k is an integer, then all these frequency bands, any frequency in which occupies any of these bands will all alias to the signal band if you sample upfront, correct? So the question now is, right? So the question now is, does this delta sigma modulator behave the continuous time delta sigma modulator behave any differently from a discrete time delta sigma? Do you understand? Alright. So first let's see what you would expect for a discrete time delta sigma modulator, and if we should expect any difference at all. In a discrete time design, this is not there. This is the sampling operation. You have Z inverse by 1 minus Z inverse. Alright. This is what you get. So, if there was a tone between 0 and 1 by 2 OSR, everything is hunky dory, you get what you expect, signal transfer function of in band signals almost equal to 1, and the NTF within the band will be will go up as omega, since we are talking about low frequency, and the output will be the signal plus shape noise. Now if the input signal here was a sine wave at 1 plus delta hertz, what happens after sampling? It is indistinguishable from a sine wave of delta hertz, So it goes through the loop, alright, and I mean as far as the loop is concerned, the signal could have been at delta hertz and nothing changes, correct? So in other words, the response to a sinusoid at delta 1 plus delta hertz is the same as the response to a sinusoid of delta hertz. So this is equivalent to saying there is aliasing, right? I mean, so you basically need some kind of anti-alias filter up front here to make sure that the response due to signals at 1 plus delta hertz is what? Is greatly attenuated compared to the response at delta hertz. Does it make sense? Okay. Now, what should you expect? Should we expect any different for the continuous time modulator? So let's find what happens to the signal transfer function. All right. So I don't know. This just involves some manipulations of the signal flow graph. Okay. See, I'm comfortable analyzing everything when everything is either discrete time or when everything is continuous time. Okay. Now this seems to be a major pain because part of the loop is discrete and part of the loop is continuous. So the easiest thing to do is what? Pardon? You separate this where you're dealing with a system where most of it is you separate it into two parts, one which operates only in the continuous time domain and one which operates only in the discrete time domain. So what do you suggest? Which is the only problematic? Which are the problematic guys here? The 1 by s is problematic. So you want to get it out of this discrete time loop. Okay, the feedback is all in discrete time, so it makes sense to get rid of the as many of the continuous time blocks from this discrete time loop as possible. So the first candidate that comes to your eye is 1 over s. So how do you get rid of 1 over s? You can push it out of the loop in this fashion. What happens here? It's 1 over s p of t. All right. Now, what else? Even now the loop is kind of half continuous and half discrete. So, any suggestions? How can I make this a continuous time system whose output is acted on completely by a discrete time system? Pardon? Can you? Okay, we'll combine 1 over s and p of t, that's fine. Anything else? What can you do to the sampler? You can pull the sampler outside the loop, okay, in this fashion. Alright. Alright. So, and there are two summers. I can actually remove one of these summers and add E of n here. Does it make sense? No black magic, it's all legal. You follow? Okay. Now, so let me remind you again that this is in principle exactly equivalent to the original continuous time sigma delta modulator that we started off with, which is this character. Alright? All that I've done is pulled stuff around the, around the summer and stuff like that, which is basically harmless in principle. So this is exactly equivalent to the original continuous time sigma delta that we had. What can you say about the transfer function from E of n to V of n? Subrato. Yeah, what is it?
1 by 1 plus 2.
Yeah, which is what? This is a first order delta sigma modulator, man. What is the transfer function from the quantization noise to the output?
1 by 1 plus Z, LZ.
Yeah, what is LZ? And
LZ is 1 by 1 minus Z inverse.
yes, so 1 by 1 plus LZ is?
It is 1.
No, the hint is this is a first order delta sigma modulator. What is the transfer function from the quantization noise to the output? Okay, forget about all this. In a first order delta sigma modulator, what is the transfer function from the quantization noise to the output?
You are asking the exact expression or the?
Yes, the exact expression. Okay, what does the first order noise transfer function look like?
1 minus Z inverse.
This is a first order delta sigma modulator, which means that it implements a first order noise transfer function, which means that the transfer function from E of n to the output V of n will be 1 minus Z inverse, which is the same as 1 by 1 plus L of Z, because L of Z is Z inverse by 1 minus Z inverse. So 1 plus L of Z is whatever, right? The right thing. Okay, you understand? This is a first order modulator. This is a remanipulated signal flow graph of the same first order modulator. So the transfer function from the quantization noise to the output still remains 1 minus Z inverse. Okay. So if the transfer function from E of n to V of n is 1 minus Z inverse, what is the transfer function from, let me call this signal auxiliary signal, I don't know, I'm running out of alphabets here. Okay, no, X is for state variables, so I don't want to use X. Okay, alright. You understand? So if the transfer function from E of n to V of n is 1 minus Z inverse, what can you say about the transfer function from R of n to V of n? Same thing, correct? So V of Z by R of Z is the same as V of Z by E of Z, which is 1 minus Z inverse, correct? Which is, let me again remind you that this is nothing but the NTF of the loop, correct? So, what is the great thing that we have done here? Is the analysis of this guy any easier or any more difficult than the earlier one? It's easier because this is now a fully discrete time system which takes inputs, from this input, which is a discrete time signal, to this output, which is also a discrete time signal. The transfer function is 1 minus Z inverse. Does this make sense? alright. Okay, now what now, but I am interested in finding what the response is to a continuous time sinusoid applied here to the output, correct? So how do I go about finding it? I will go in stages. What is the response from, so this is continuous time input frequency, capital omega, okay. So if I put in a sinusoid whose frequency is going on varying, alright, what will be the magnitude response as of R of t? R of t is nothing but the integrated version of u of t. If the input is a unit amplitude sinusoid and I keep varying, or in other words I am basically looking for the frequency response of the integrator, correct? So if I plot it on a linear scale, what will it be? No 20 dB, this is a linear scale. Let me call this 1, this is 0, alright, omega by 2 pi rather. Or rather, let me just, make this 2 pi so that this becomes 1 hertz. Alright, so at DC what is the gain of 1 over S? Infinity, so it falls off as 1 by capital omega, right? So alright, so this is R of j omega, correct? Now if I put in a sinusoid at frequency delta, rather 2 pi delta, what is the output R of j capital omega? 1 over, the magnitude is 1 over 2 pi delta, correct? Now this gets sampled, so what happens to the equivalent sampled stuff? It will alias to? Think carefully. The input, the sampling rate is 2 pi hertz, 2 pi radians per second. Come on people. 1 hertz goes to 2 pi radians once you sample. So 2 pi, what do you call, delta goes to 2 pi delta. Okay, alright. So since the sampling rate is 1 hertz, the frequency axis can be interpreted as either a continuous time or discrete time. It is the same, happens to be the same number. Okay, does it make sense? Okay, now what happens to, I mean that's not the end of the story, right? So this is what happens to, this is the amplitude of the sinusoid after sampling, correct? Then is that all there is to it, or I need to find what comes out at V? So what should I do? Sandeep. Okay, what have we done so far? We have put in a sinusoid at angular frequency 2 pi delta, or in hertz, delta hertz. We are now at this point, we have traced what happens to the sinusoid when it comes here, okay. Then we have traced what happens to the sinusoid when it comes here, alright. So, and we have concluded that at this point, the input sinusoid of frequency delta hertz looks like a discrete time sinusoid of radian frequency 2 pi delta, okay, with an amplitude which is small or large, which is very large because delta is very small, okay, and the amplitude is 1 by 2 pi delta. Does this make sense? Okay, alright. Now what is the next job? To trace it through this block here, alright, and what is the frequency response of that block? 1 by 1 minus Z inverse, okay, and what happens? How does 1 minus Z inverse look like? Yes, people. Starts. This reaches 2 at pi, okay, 0 at 2 pi, and this keeps repeating, correct? So what is the output V? This is nothing but the NTF magnitude, correct? So what should I do? I should multiply this sinusoid by this gain, correct? So V of e to the j omega is nothing but the amplitude of the discrete time sinusoid at the input, which happens to be 1 over 2 pi delta times one minus e to the minus j omega, where omega is 2 pi delta. Does it make sense? Alright, and for small delta, what is this? 1 over 2 pi delta, and for small delta, what is 1 minus e to the minus j 2 pi delta? Modulus of this 2 pi delta, which is equal to 1. Does it make sense? Alright. So, as we expect, if you put in a low frequency sinusoid, the magnitude of the signal transfer function is 1. Okay? Does that make sense? Okay, another way of looking at the same thing is the following. At very low frequencies, what did we say? I mean, this is nothing but the loop filter L of j capital omega. Okay, and this is the transfer function from here, from R of n to the output is nothing but NTF, correct? So it is, we found that we find in other words that this thing, okay, multiplied by alright, and at very low frequencies, what can you say about this guy and this guy? At very low frequencies, where the gain of the loop gain of the filter is very, very high, okay, or the loop gain of the loop is very high, which basically means that the filter in the forward path has a very high gain. The NTF is nothing but approximately 1 by the gain of the filter, correct? So the gain of the filter times 1 over the gain of the filter is approximately is 1. Does it make sense? Okay. So at very low frequencies, the gain of the signal transfer function magnitude will be 1. Okay. Alright. Now let's take a look at a sinusoid which is at 1 plus delta hertz. Okay. So what happens? Let's trace it down through the through this model which we have derived. So what happens to what happens here? Pardon? It will be 1 by 2 pi times. Okay, why are we interested in a tone at 2 pi times 1 plus delta O5 BTEC? Yeah, why? I mean, we want to see what happens to a tone in the alias band, correct? And we know that in a regular data converter, a tone at delta will also, a tone at 1 plus delta will alias to delta when sampled at 1 hertz, correct? Here we expect to see something different. We don't know whether it will be worse or better, okay? We thought it would be better based on some very rough arguments. We will quantify the difference now. So, where is 2 pi times 1 plus delta? It is just after the notch here. Okay. This is 2 pi times 1 plus delta hertz. 2 pi times 1 plus delta radians per second corresponding to a hertz of 1 plus delta. So that passes through the integrator and the magnitude here will be V of e to the j omega is 1 over 2 pi times 1 plus delta, correct, times what happens after the sampling? It will so the amplitude of the sinusoid here is 1 by 2 pi times 1 plus delta, okay, and the frequency is 1 plus delta hertz. The moment you sample it at a rate 1 hertz, it behaves like a sinusoid. You cannot distinguish from a sinusoid at frequency delta, okay. So then what happens? You have to multiply it by the magnitude of the NTF at 2 pi delta, and we know which is equivalent to multiplying it by this magnitude, but we know that this stuff repeats, so it is equivalent to multiplying it by this guy here. Alright, and what is that? It's 1 minus e to the minus j 2 pi delta, which is approximately equal to 1 over 2 pi times 1 plus delta times 2 pi delta, which is delta by 1 plus delta. Does it make sense? So what can you say about the magnitude of the signal transfer function for the alias band?
Approximately versus delta.
It is approximately delta, okay, and so is that small or large? It is very small, okay. Does it make sense? So in other words, the alias rejection, which is defined as the response to a tone at 2 pi plus, I mean the alias rejection can be defined as the response due to a tone at delta to the response due to a tone at 1 plus delta, which corresponds to the first alias band, okay, can be can be graphically figured out, seen to be, see the NTF is a common factor in both calculations, correct. So what is the delta? What is the it is simply so the alias rejection is basically does it make sense? Okay. So what can you say of the alias rejection to a tone at 2 plus delta? It will be delta upon 2 plus delta. Okay, so you can see that higher order aliasing bands get attenuated to a larger degree. Okay, and this makes intuitive sense because we realize that the loop gain or the loop filter gain is dramatically dropping with frequency. Okay, so even though there is aliasing, the sampling is happening after the loop filter. Okay, which basically means that the loop filter cannot respond as quickly or with as large a strength to alias frequencies as it can with for frequencies within the band, which means that the alias response of the continuous time delta sigma modulator is actually significant. Okay, this we have just done a first order example. Okay, it will become clearer later on that when you have higher order, this becomes even better. Okay, all right. So what else do I have to add? So what is the bottom line now? So the response to frequencies around the alias bands is actually much smaller than in band frequencies. Does it make sense? Okay, which means that there is implicit anti-aliasing. All right. In fact, at the center of the band, that is at DC frequency, the aliasing is zero. What is the alias rejection? Infinite, because the gain for the alias, if delta becomes 0, this will turn here. This gain will go to infinity. So one way of understanding it is the ratio of this guy which has gone to infinity to this value here, which is infinity. Correct? All right. You understand? So alternative expressions for this alias rejection. The response at so if I take a general sigma delta modulator with L of j omega, magnitude of the response STF at a sinusoid at delta hertz is nothing but L of j omega multiplied by L evaluated at 2 pi delta hertz, okay, multiplied by the NTF evaluated at 2 pi delta, correct, and this is approximately how much? The NTF at low frequencies is approximately 1 over the loop gain. Why is it 1 over the loop gain? Because it is actually 1 by 1 plus loop gain, but if the loop gain is very, very large, it is 1 over loop gain, correct. So this is approximately equal to 1, okay. On the other hand, the STF for a sinusoid at 1 plus delta hertz is mod of L of 2 pi times 1 plus delta times NTF of 2 pi delta, alright. Okay, and what is NTF of 2 pi delta? It is nothing but 1 over L of 2 pi delta, okay. Does it make sense? Yes. Oh, well, no, when I derived this, I'm not supposed to have had it in mind, but, okay. So, no, I mean, yeah, I think people discovered this by accident. That's my take, but I'm not sure. See, systems like this, right, where you have continuous time stuff and then there's discrete time stuff in the loop, have been known for a long time. Okay, it comes about. There's this whole area of control systems called discrete data systems, and the origin of these things happens because a lot of times in control, a lot of this control is applied to chemical plants. Okay, so yeah, the plant is it's got valves and all sorts of complicated looking stuff, but the control is best done numerically, right? So you have a computer which basically goes on looking at the various outputs of, in other words, the various states of the chemical plant, and applies appropriate control inputs to go and fix the, make sure that the chemical plant is running as it's supposed to do, right? So, in other words, the various states are sampled and then you apply control through that stuff. I mean, so even though the main plant is analog, a lot of the control is all done based on sample data signals. Okay, so so such systems have been known in control for a long time, and in control typically all these plants are running at very, very low rates. So even though within quotes this is sampled, the sampling rate is so high that it virtually looks like for all practical purposes it looks like continuous time. So a lot of the analysis also kind of hacks from continuous time stuff, though there is a very definite theory for continuous time systems embedded within discrete time feedback loops. Okay, I think my take on this is that people discovered this somewhat by accident rather, and you can see that it's not very difficult to derive. Okay, so and the moment the guy designed one thing and put it in the lab, I'm sure you would have seen definitely that the response to the alias tone would be much smaller, which means that then he'll go take a piece of pen and paper and then figure out what it is, and notices that it is much better, and then tells the world about it, and suddenly everybody is excited because you can get rid of the anti-alias filter. So this is a big plus. Okay, and please notice that in an anti-alias filter what you need is in principle notches in all the alias bands, correct? You don't really care too much about what happens elsewhere as long as the alias bands are all notched out, and dramatically that's exactly what this is doing for you, because in the alias bands the NTF is 0, correct? I mean in the middle of the alias bands rather. See, these are all the alias bands, this and multiples of 2 pi, and you can see that at all these multiple frequencies the NTF is very small, because that's what you are depending on to do noise shaping in the first place. So whatever you do, you will make sure that this is very small if you want your modulator to work, okay, and that gives you naturally notches in the signal transfer function at all alias bands. You understand? So I think this is serendipity rather than anything else, okay. It's not very often that this happens, okay, that you do something and for something else and it helps you precisely where you want, okay. So okay, so from this relationship and this relationship you see that the alias rejection is L of 2 pi into 1 plus delta divided by magnitude of the loop filter gain at 2 pi delta, okay. Alias rejection, I mean you're saying this must be a large number, okay, so yeah, whatever, you get the idea, right? If you take in dB, then it's just minus. Alright, the physical intuition is that the loop gain is much higher for a low frequency sinusoid than it is for a alias band sinusoid, which means that the loop is dead at frequencies around potential at all alias bands, which means that you're doing very well. Okay, and as delta goes to 0, you can see that this guy goes to infinity, because at DC you have the loop filter has got infinite gain. So at all multiples of 2 pi you will in fact have a notch. Okay. The last thing I wanted to add was, so now can you summarize what you think will, so this is, so if I now draw the loop filter gain on a log scale for a first order system, it will do this, okay, this is a straight line, assume it's a straight line, okay. So this is first order. If you want a second order, what do you think it will do? The loop filter will do something like this and something like this, okay. Please note that no higher order system can be stable if at the time it crosses 0 dB the slope is 20 dB per decade. That I think I mean, say at high frequencies every closed loop system must look like a first order system, okay, because if it looks like a second order system around here, the phase of that must be 180 degrees, which means it's close to getting unstable. So the only thing the higher order system is doing is basically increasing low frequency gain, okay. So let me, this is first order, this is second order, and third order will do this, it will become third order for sometimes somewhat second order and then do first order and so on. So for a second order system, this is how the loop filter magnitude response will look like, which we'll again derive later on again anyway formally, but this is what you can expect. So what do you think will happen to the alias rejection? The alias rejection, the first order case was say So this was 2 into 1 plus delta, and this is delta. This is the alias rejection. Okay. For a second order system, it will be this chap here. The distance is delta, the gain is much higher, so the alias rejection also get higher. And this makes sense because you have two integrators in the loop. Okay, the ratio of the gain at high frequency to low frequency will be much larger because you have two low frequency amplifiers. For low frequency, you have both amplified. For high frequency, both integrators attenuate, so it's a double whammy for the alias. Okay, right? And it also makes sense from an application point of view because if you use the second order modulator to begin with, that basically means that the in-band quantization noise is much smaller than what you would have got for a first order modulator, right? Which means that your alias rejection also should get better. You want it to get better because it doesn't help to have a great converter but poor alias performance because noise from all those bands will just get into the signal band. Okay, and this naturally just works like this, which is a very nice thing. So this is a very, very attractive feature of continuous time delta sigma modulators, which is making it more and more popular in the area of data converters. Somebody recently told me that in the last 10 years, of all the data converter papers that were published, 40% happened to be delta sigma converters. So you can see there's a lot of interest in the area. And over the last 3-4 years at least, I've seen a lot of the delta sigma converters are all being done in continuous time. Okay, so we'll stop.